Hello and a good morning or a good afternoon, and welcome to our webinar for this week. Today we will be discussing the topic DC and AC system protection with Fronius inverters. And joining me today are my colleagues, starting with Cyprian Okolo, our technical sales advisor for the Western African region. He's based in Lagos, Nigeria, as well as Belon Kotza. He's our technical sales advisor for the Southern African region. He's based in Johannesburg, South Africa, as well as myself, David Mwangi. I'm the technical sales advisor for the Eastern African region. I'm based in Nairobi, Kenya. So we will be doing this presentation, and Byron will be offering you chat support for all the questions that you have. Today's agenda looks as follows. So we will talk about protection classes. We will also look at DC isolation, then we go to the DC switch. We look at the Fronius solutions and the possibilities of electrofitting, the various solutions that are available from Fronius. We will also check and have an overview on lightning protection for PV systems. Then after that, we go into reverse current, string fuses, reverse polarity of strings, AC or grid system protection, and then we look at how that AC or grid system protection works with the Fronius inverter, and then how do you then install the grid system protection. And then after that, we will give you further information. So let's get started and look at the protection classes. So when it comes to protection classes, there are basically three. So we have class 1, 2, and 3. And class 1 is with reference to grounded circuits. Class 2 is looking at double insulated circuits, and class 3 would be for extra low voltage circuits. So these protection classes are of course applied for both AC and DC systems, and for grid connected system or PV systems. And protection class 1 and 2 would be just enough. Class 3 would most likely be used for data communication lines and things like that, for RS 485 and similar communication protocols. So looking deeper at class 1, this should be able to provide adequate fault protection, and therefore the following measures are usually applied or taken. So we have a single isolation of cables or circuits. Then you have grounding of metallic parts, e.g. the chassis of an inverter or any other electric equipment. And this comes also in combination with overcurrent devices or residual current devices. And therefore, if you are to implement something like this, the schematic for connection would look like this. And therefore, the overcurrent device would open up if there is a leakage current to the ground or earthing cabling. When it comes to protection class number 2, this should also be able to provide adequate fault protection, usually having taken the following measures. And you'd have then to have double or reinforced insulation of cables or circuits. Additional measures would also be taken so that the PV cables that are normally exposed to harsh environmental conditions, which would include heat, ice, or UV rays, are kept within operational or good operational conditions for the expected duration time of the PV system, which normally is anywhere between 20 to 30 years. So in protection class 2, the inverter, especially transformerless inverters, must be able to check the isolation monitoring, and therefore this is checking the isolation between the plus and the minus terminals of the inverter connection, as well as integrating a residual current monitoring device. So also this is for the transformerless inverters. Let's have a closer look at the DC isolation and what this is all about. So for protection in class 1 systems, one of the following can be used as a protection measure. So you can have what we refer to as GFDI, or the ground fault detector interrupter, and also impedance grounding. When it comes to the GFDI, this can be achieved in different ways. And it's quite common to have a DC fuse in the range of 1 to 3 amps. Of course, this depends on the size of the system that has to be protected. And the protection functions as follows. So if there is a ground fault, the fuse or the current monitoring device opens up, and therefore the leakage current is able to go to the ground. So there is also what we refer to as the non-detection zone of a GFDI protection system. So, and the design of the GFDI has two inherent implications. One is that it's not a suitable protection system that is sufficient for protecting humans, because 1 amp is already too high for a human to be exposed to. So therefore, if a fault occurs in the earth conductor, it will not be recognized. Another fault might, result or become a hazard. So therefore, the remedy that is taken is to use class 2 protection scheme, and a GFDI must be able to disconnect the ground connection before the start of operation and detect if there is a ground fault in the grounded part of the system. So therefore, this would be a simple schematic showing how such a GFDI protection system is integrated. We also have what we refer to as impedance grounding. So in this case, the system is grounded by a high impedance, which limits the fault current to a certain less dangerous limit. So therefore, in this range, we are talking about a protection system that would also be adequate for protecting people from getting electric shocks. So a typical limit in this case is about 30 milliamperes. So if you consider current is equal to voltage over the resistance, then the impedance for this kind of ground impedance protection system would be about 30 kilo ohms, considering that you have an input voltage of up to 900 volts on the DC side. So below here, we can see how such a ground impedance protection system is applied. And therefore, as mentioned here, because we are limiting the fault current to a maximum of 30 milliamps, then this offers better protection against people or maybe even animals getting electric shocks from the electric equipment. So let's now have a look at the class 2 protection systems. So for transformer-based inverters, the inverter usually measures the impedance to ground from the positive and the negative via an impedance network. If this impedance value decreases to a value that is below several hundred kilo ohms, then a warning is displayed in the inverter. On the flip side, for transformerless inverters, so this becomes even more important to check the impedance to the ground. So the inverter will measure the impedance to the ground from both the positive and the negative before connection to the grid. That is, every morning, a transformerless inverter, before it starts working, when the sun is already producing power through the panels, this impedance measurement or isolation measurement will be done by the inverter. And during this operation, the RCMU, what we refer to as a residual current monitoring unit, which is by default integrated in a transformerless inverter, detects the value of the residual current on the DC side. If this value of the residual current is above 300 milliamps or is rapidly changing by steps of 300 milliamps, then the inverter by grid code operations is required to switch off. So this function cannot be achieved by using the commercially available RCTs or the residual current devices, since such units are not able to detect these jumps in the in the current or in the leakage currents. Let's now look at the DC switch. So this is a surge protection, getting into the area of surge protection for increased or maximum safety of the system. So when it comes to the DC side, there are some isolation requirements that are relating to, for instance, some standards, that is IEC 603-64-7-712. And therefore, this requirement is to have a means of isolation on the DC side. So, and this standard is usually sort of a standard across many parts of the world. So some of the details in this standard or in this requirement means that you must have a means of isolation so as to allow maintenance of the inverter. So if you're going to do, for instance, some maintenance work or service work on a Fronius inverter, as you know, you can do replacement of boards and stuff like that. By requirements, you should have a way of isolating the DC power that is coming to the inverter. So also a DC disconnector switch that is now being used for that purpose must be capable or to interrupt or to withstand the maximum power that can be generated on the DC side, as well as the full voltage that is coming from the DC side. And then a combination of devices is allowed to provide for switching. So this can be by a manual switch or isolation by things like DC plugs. If you're looking at things like MC4 plugs as well, this can be used as well for isolating the DC part of the system. Having said all that, so we can ask ourselves, what is the Fronius solution that is offered, and what are the possibilities of retrofitting? So we have the possibility for protection on the DC side of the Fronius system using surge protectors. And these surge protectors are divided into two classes: for the smaller inverters up to 8.2 kilowatts, and then for the bigger inverters from 10 kilowatts going up. For the smaller inverters up to 8.2 kilowatts, we have DC surge arrestor types 1+2 M version, and therefore this means that this is a DC surge protector or arrestor that can be configured or integrated for an inverter with 2 MPPTs. As we know, Fronius inverters either have one or 2 MPPTs. And then this is available as a retrofit kit. So, and you have to do some hardware adaptation when you do the retrofitting of the DC surge arrestor into the smaller inverters. For the bigger inverters, we have 2 or 4 technical designs possible, but broadly covering the 2 types of surge arrestors. We have the type 1+2 that can be done for both single and multi-version, multi-MPPT version of the Fronius inverter. And therefore there we are talking about both the SIMO and the Echo 25 and 27 kilowatt inverters. And you also have the DC surge arrestor type 2 that is also capable to be retrofitted, all to be ordered ex-factory for a single MPPT or multi-version of the inverter. It's also available for retrofitting because this is an option that you order the inverter with. So we highly recommend to always order the inverters with DC OVPs or surge arrestors. And yeah, so that you do not have to do anything when you are going to install the inverter, or you don't actually forget to do the DC side protection when you're going to install the inverter. So when it comes to, for instance, as another example, the Fronius Gen 24 Plus inverter, we also have the possibility for DC SPD type 1+2. This is only available as a retrofit kit. It's not possible to order the inverter with the DC SPD ex-factory. So the SPDs, as we can see here on this photo, are actually mounted on a print board, which you're then going to retrofit into the Gen 24 Plus inverter. So there is a provision that is made for retrofitting the print board with the SPDs. So if you're not buying directly from Fronius and you're going through a sales partner or distribution network, then these retrofit kits for Gen 24 plus inverters can be ordered through our wholesalers or distributors. Let's now have a look at lightning protection for PV systems. So when it comes to damages that can cause failure to PV systems, surge damage is one of the biggest causes of concern. So the most frequent cause of damage to PV system, as you can see in this pie chart, and these are caused by short-term or transient surges that are recorded in microseconds. So as we know, lightning discharge as well as electrostatic discharges as well as switching operations can cause these transient surges within a system. These transient surges will then affect both the hardware as well as the software in a system. And if there is no protection, as we have seen with the surge arresters, then this ultimately will lead to failure of the entire system. So looking at this pie chart, we can see the classifications of the various causes of damages to PV systems. So we can see at around 18% of the common cases are related to these surges that we are said are both short-term lightning transient surges, which are both discharges from lightning, electrostatic discharge, as well as if you are switching off your or on your appliances or systems when they are still loaded. The other causes of failures are not our concern for today, but you can see that there is quite a good probability that you do not have enough protection in your system. Then these surges can actually be a big cause of concern. So having a closer look still at the data that is coming from the lightning side as far as the surge damage is concerned, it would be good to understand what is the lightning density of that particular area where the system is installed. And this lightning density is evaluated by looking at the lightning strikes the NG charts, as you can see here to the right. As an example, we have a region in Central Africa that is called Kifuka, and this is the most prone area to lightning strike. For every square kilometer, they receive about 154 strikes every year, and therefore, if you are going to do your installation within any part of the sub-Saharan Africa region, then you can see that there is a huge probability that you're going to have a lightning strike from one time to the other. So each strike is therefore a potential risk for electronic damage, especially to inverters. But this can also be something that is going to affect your PV array if the lightning is not properly arrested. So the question we can ask ourselves is, what happens in the case of a lightning strike? So we can see that we have, as mentioned before, what we refer to as transient surges. And these are not things that are foreseeable and not periodical voltages, currents, or loads. So by division, you can have several parts of a lightning that can be analyzed. And we have what we refer to as the leader charge. Then the leader charge and the catch-up charge will build up the main lightning discharge. Then you have the part of the lighting that we refer to as the impulse currents, as well as the long-time currents. So we can see here that the impulse current are also quite big. They are operating from, as you can see in this graph, for instance, from 9 kiloamps up to 30 kiloamps in some instances. We also have, and these are within microseconds of time measurements, but you have the long-time discharge, which can be quite destructive, and this is actually what also causes fires. So we have the discharge that is happening over several circuits. So we can see, for instance, in this graph, the discharge, what we are referring here as the long-term current, is happening within about 2 seconds or 2.5 seconds. So, and the maximum current here is recorded at 400 amps. So 400 amps that are not properly arrested can cause some significant damage to anything that the lightning strikes. So we can also look at the AC side surges that can also be as a result of lightning strikes. And the AC side surges will damage varistas on the AC side of the inverter. It can be as a result of indirect lightning strikes. As you know, when you have a lightning strike to the ground, it's possible that some of those discharges will travel through the earthing cable of the premises, and one way or the other, this discharge can also be seen at the inverter connection point through the grounding cable. So when you have this kind of problems, it could also indicate that you have a bad or missing connection of the neutral conductor, or surges on the AC grid, that is the public grid where the inverter is connected to. Because also these lines on the public grid, because they are exposed when they are carrying the voltage through, they do receive also occasionally some lightning strikes. So these can be sources of surges. Possible, but the most commonly used one are the lightning arresters, and these are for arresting these charges before they discharge to your equipment. If you have, therefore, unfortunately, damage to the varistas as a result of a lightning strike, then that kind of damage for the inverter will not be covered under the Fronius warranty terms and conditions. So here on the right, we can see what are the characteristics of surge arresters. So here we have the total current in the gray curve, and then we can see what is traveling through the lightning arrestor and the portion of that total current from the surge that is traveling through the varistor. So when you do not have the arrestor, it means that the varistor is going to take the entire current, and therefore that can very easily result in damage. So how then to optimally protect a PV system from a Fronius perspective? Number one, we do recommend that you do grounding and potential equalization. So this equalization will be the base of each surge protection system. And we do recommend that you keep your grounding resistance as low as possible to something that is below 10 ohms. When it comes to the connection of cables and the arrangement thereof, we do recommend no cable routing. Keep conductor loops as short or small as possible, and then have separation of protected and protected cables. And this also applies to data cables, especially if you have several inverters connected together. Try as much as possible to separate the data line cables for Modbus communication or the solar net ring from the cables that are carrying the electric current. You can also integrate external lightning protection. So this will be like an interception system and arrest the lightning discharges. So this can be integrated as an overall protection system for the PV system. And in some jurisdictions, this is a normative requirement. So if you do require to integrate lightning protection for either your house or your PV system, then we do also recommend here getting in touch with the lightning protection experts, because there are some organizations that are dealing only with lightning protection, and there you can get a lot of valuable advice on the best way to achieve it. When it comes to internal lightning protection, we have the potential equalization with SPDs, as we have seen with surge arresters that are inbuilt into Fronius inverters. And these are, of course, integrated as an option to the various inverters that you order from Fronius. So therefore, what factors are to be considered for overvoltage protection if you want to increase the safety of your system? So we have a few things that you need to look at. You have to look at the internal lightning protection, what you have said regarding potential equalization. Minimize the probability of damage, therefore by this lightning protection. So you increase the economy of your system. There are higher yields because the system uptime is improved, and there are no reinvestments when you have thought about things like lightning protection right before you install the system. Also, when it comes to insurance, you might have higher insurance premiums when no proper overvoltage protection is shown for your system. And then in terms of inverter protection, that becomes a factor of safety as far as the inverter operation is concerned. Then for Fronius inverters, as we have seen, if you do require at any one point, if you had not ordered the inverter with OVPs, then you can very simply retrofit OVPs into any Fronius inverter. So let's now have a look at the topology of SPDs. So as mentioned, we have type 1 plus 2. We also have type 2, and we also have what we refer to as type 3. So type 1 plus 2 is a combination arrestor, and this offers both coarse and middle protection. And it can do lightning strike current arresting and surge protection as one device. This is normally installed or retrofitted at the feeding point after the energy meter. So as we saw within Fronius inverters, this is always done also in combination with the earthing conductor. And in terms of the voltage range, the type 1 plus 2 SPDs can handle a voltage from around 1,300 to 6,000 volts. When it comes to type 2 surge arrestor, this offers middle protection. So it's like a sort of the next grade of protection from the type 1 plus 2. And in terms of the residual voltage, this is offering protection or can withstand voltages from about 600 to 2,000 volts. Looking at type 3, these are for fine protection of electronic devices and can be effective in elimination of small surges. So these are mostly done in-house, and for compensation of big surges, it's recommended that you use type 3 SPDs in combination with either type 2 or type 1 plus 2. So these type 3 are mostly what are used for data line protection. So we also have to understand the difference between the overvoltage category, which you are looking at now, and overvoltage protection, what we refer to as surge protection. So the overvoltage categories are about 4. So we have what we have category 1, 2, 3, and 4. And the difference is the peak voltage strength for each class rating. And the classification depends on the materials as far as insulation resistance is concerned. In addition to that, we also have to consider what is the type of network link. As you can see to the right here, for category 1, we are talking about a rating or a class of surge voltage maximum 1,500 volts. And this is something that can be applied for laptops and phones. Class 2 is dealing with up to 2,500 volts, and this is for household appliances. Class 3, maximum 4,000 volts for fixed installations with a continuous connection. And Class 4 offering the highest protection with 6,000 volts, a connection point for installations, e.g. the energy meters, like Fronius smart meters or grid meters. So for Fronius inverters, we have overvoltage category on the DC side of class 2 and on the AC side of class 3. So therefore, you can see that the Fronius inverters are adequately protected as far as the voltage categories are concerned. So we also have to look at, as far as protecting the system is concerned, the effects of reverse current, and quickly going through what reverse current looks like. Reverse current is when you have a cell of a module operating as a consumer instead of a producer. So to the right here, we can see a graph of a solar module or an IV curve. So this unshaded area here is the normal operation as far as the production of a solar cell is concerned. So when it starts consuming power, so we have a negative current or voltage going through the cell or the module, then that module or cell becomes a consumer. So it can occur when you have parallel strings with different open circuit voltages, and fault examples can be short circuits in one or more modules. It can be a short circuit in one or more cells of a module. It can be a double ground fault in one module or in the cabling. And the consequences of reverse current would be to destroy a solar module if the reverse current flows for a long duration of time, and that this damage is going to happen as a result of creation of hotspots within the solar module. So there have been studies that have been done by, of course, independent test labs such as the Fraunhofer Institute. And what they have found is that as a general rule of thumb, most modules are protected against 2 times the possible short circuit current. But they also studied an exposure of about 7 times the short circuit current for about 1 hour, which resulted in no damage to the PV modules that were being tested. But of course, we do not recommend that you have the possibility of reverse currents in your systems, and therefore this has to be protected. So the modules do try to protect this by integrating bypass diodes. So therefore, this is something that should always be monitored because if it happens for a long duration of time, then a big part of the PV array can easily be damaged. So at this point, I would like to hand over to Cyprian to continue with the next part of the presentation. So Cyprian.
Yes, indeed. Thanks a lot, David, for your presentation. I will now show my screen and continue with the rest of the presentation. So I believe that you all can see my screen and hear me clearly as we continue. So we shall be continuing with string fuses as part of protection for PV system. So straight up, let's continue with the description of what a fuse looks like. So, and the best way to describe it is looking at the structure. So from the structure of the fuse, as you can see from this particular illustration, we can see that it is made up of housing, the fuse wire, and then what we call the arc chute or surge suppressant. So as you can see in this case, we have 2 metal contacts that actually acts as the continuity point for flow of electricity. And then we have the fuse wire, which is of course responsible for triggering or rupturing in case of the unwanted current or fault current passing through. And then of course we now have in this particular example, the quartz sand that is responsible for suppressing the arc, because for every rupture of a fuse, it of course comes with a considerable amount of electrical arcing. So this arc is the best practice is to suppress it. So in this case, for this particular example, for this fuse, the quartz sand is used for suppressing this arc accompanied with the rupture. So basically, describing the function of a fuse is for the wire to rupture or to melt in the case of overload or short circuit current cases. And then this occurrence, of course, yields or results in an electric arc, as earlier mentioned. And then this is, of course, taken care of by what we call electric arc chute or electric arc suppressant. Good. So going forward, we're going to be talking about string fuse categories. We have several categories out there, but then we shall be discussing the two major categories, which is the AR and then the GR. The AR basically describes the partial range protection, and then of course this is usually applied for short circuit protection only, and of course is not recommended for PV systems. This is as we're going to see later, because it is not adequate for PV system protection. As you can see in this description, once the nominal voltage, nominal current is exceeded, it gets into what we call the unsafe zone. And then typically, short circuit currents tend to come in 3 times, in the amount of 3 times, or so between 3 times to 8 times of the nominal current. And of course, this is way, way high for PV systems, and of course will eventually cause some damages because the termination of the arc in this case is not guaranteed. But then next up, we're talking about the full range protection, otherwise denoted as GR. This finds its application in areas of short circuit and overload current protection. So this is what is recommended for use in PV systems. So in this case, and as you can see from the illustration, the nominal current doesn't need to be exceeded that much before the termination of the arc occurs. So we're going to be explaining more about this in the next slide. As you can see in this case, there's of course an IEC standard recommended for this. As you can see, 609 IEC standard 609.269-9. So it is of course recommended that only GR fuses are to be used. GR rated fuses are to be used with for PV systems. And then of course, in order to make sure of this, please look out for fuses that have this logo or tagged GR or GPV, of course, followed by this sign, as in that's the PV icon. Please ensure that the fuse you use for PV systems follow these recommendations as given. Good. So in order to describe what I was saying earlier, for the nominal current, fault current usually are in the region of 1.13 to 1.45, the value of the nominal current, as you can see. So this, of course, ensures the activation of the fuse wire or the fuse to rupture and protect the system when these particular values are reached. Good. In order to buttress this point, we have a graph here. It's a normal inverse graph that depicts the reaction of string fuses. And this is basically an average current time curve, which describes the turn-off time of the fuse. So this is given by fuse time plus arc termination time. So for this particular example, we can see that for this particular fuse in question, system in question, there's a nominal current of 1 amp and an overload current of 3 amps. Then the turn-off time is 0.08 seconds. So to actually shed more light on this, we can just have a bit of a zoom on this so that we could really understand what is happening here. So for the overload current, as already seen here, it is going to activate faster than than usual because of the high current. So for a current of 3 amps, if you follow this red line, so this is 3 amps. So if we follow this red line and then trace it from where it touches the curve, we are now going to get the time it will take for it to turn off or to rupture. So which is given by this particular point here. And that is what is depicting here, the 0.08 that has been depicted here earlier. So that's basically the description of this particular time graph. So in order to have an idea of the value of what string fuse should be, this can actually be gotten by the value of the nominal voltage. So for the nominal voltage, it can actually be obtained by this particular relation to ensure that the nominal voltage to ensure that it is greater than or equal to the maximum DC voltage of the inverter. And then this is also more precisely given by the voltage efficiency of the PV generator at the lowest temperature. If you could recall, in a previous presentation that we've done, previous webinar, the voltage coefficient of temperature is they're actually inversely related. So this means that the lower the temperature, then I'm going to have an efficiency or the voltage efficiency of that particular PV system in question. So let's now go for the nominal current. So in order to calculate the nominal current, the derating factors would have to be considered. So, and basically there are 4 derating factors that influence fuse characteristics. So they include the alternating load factor. This is actually a static factor for PV systems and usually has a value of 0.9. And then we have what we call the interrupting factor, also a static factor, and is defined by the manufacturer, and of course would be found on the data sheet of the fuse in question. And then we have what we call the temperature derating factor. This is a dynamic factor, also mentioned in the data sheet. And then we now have another factor, which is the fuse arrangement, which is also dynamic, and of course depends on the number of fuse holders that are installed or situated side by side. So for string control, basically the fuse factor is usually 1, and then of course these values can of course be obtained from the average time curves of the fuse to be used. So still talking about protection, we shall still also look at reverse polarity, as earlier mentioned by David. So in terms of reverse polarity, it can actually cause damage and in fact fire at the terminal point, as can be seen in this particular picture or screenshot here. So in order to prevent this, the string fuses need to act fast. So, but then in order for it to do so, it has to be properly calculated and properly placed for each system. So in order to do this, we have some recommendations. So nominal current of the fuse should not be greater or higher than the short circuit current, because if this happens, the fuse of course will not trigger. And then the nominal fuse voltage should be higher than the string voltage for arc termination. So we shall have some examples to buttress this point. So for this case, we have a correct installation without reverse polarity. As you can see, of course, meeting the earlier stated conditions of nominal voltage and current. So in this case, we have fuse rated 12 amps and 900 volts. We have the branch current for each string at 6 amps. So the summation of all the branch current gives us 30 amps. And then the voltage of each string in parallel is 350. So the summation is 350. And then this is, of course, the current summation of current and voltage of the system of the power coming to the inverter. So another point now is to describe what happens with reverse polarity. So in this case, you can see the installation of 3 amps reverse polarity of a single string. In this case, the fuse does not trigger. Why? That's because simply because if you can look closely here, because this is the string that has been reversed. So just to make it simple, the fault current here is less than 12 amps, so it will definitely not trigger. And if this happens, the fault current, of course, passes through and then, of course, destroys or damages the modules in this string. So, and then we now have another example to, of course, verify the effectiveness of correct calculation and of the string fuse. So the installation of a 3.75 amps reverse polarity of a single string in this case, when correctly dimensioned, we can see that we have the fault current of 15 amps in this case. So since it is of course higher than the string, the string fuse specification, the fuse will definitely rupture and thereby protecting this particular string from any damage. Good. So we've actually been discussing so much about DC system. So let's now have a bit of a look on the AC side. So we're going to have that look right now with AC, or what we call the grid system protection. So we're going to start off with a basic definition of what an AC or what a grid system protection means. So it's basically a protective device that constantly monitors the voltage and frequency of the grid, of course, at the feeding point for a specific switch-off conditions. So once these switch-off conditions are met, the device will definitely activate. The GS protection, as it will eventually be called for the rest of the webinar, the GS protection disconnects the PV system fail-safe mode by acting on the interface switch in the inverter, which we are going to see subsequently. The interface switch is usually consists of two electrical switch gears that are connected in series. So before we do that, let's of course point out here that there are normative requirements for grid and system GS protection from country to country. So please ensure that you contact your grid operators to confirm what these requirements are. So and to continue, there are basically three variants that we are going to be discussing in this particular presentation. So for the sake of simplicity, the topic for GS protection topic discussed in this webinar is using the example of Germany with the respective code, VDE code. Good. Let's now talk about variant one. In this case, we have the inverter integrated GS protection. This is usually integrated in every typical inverter. So for systems up to a certain capacity, in Germany, as an example, as earlier stated, for systems up to 30 kilowatts, the integrated GS protection, which acts on the integrated interface switch, can be used. So as you can see in this case, we have the already integrated GS protection, which now acts on the interface switch in series, as you can see in this case. So for this, no external GS protection is required. For variant 2, we have a centrally located GS protection relay, which also has a central interface switch. So for certain plant size, typically between 30 to 135 kilowatts, a central GS protection device must be used or implemented. And then this is how it is implemented. So both are actually externally integrated. So the central GS protection relay acts on a central interface switch that protects the inverter. So both components are installed externally. Good. So the third variant, in this case, we have a central grid and system protection, that protection relay that controls or acts on the already integrated interface switch, as you can see in this case. And I must say here that this is usually what is implemented with Fronius inverters. So no additional interface switch has to be installed. All you need is the protection, GS protection relay. And then this, of course, is connected to the interface switch already integrated inside the inverter. So we're going to be shedding more light on this particular protection scheme. So how does it work with the inverters? So first off, let's just to give us a list of the inverters, possibility of inverters. So depending on the plant size, this usually have application in our commercial inverters, ranging from the SIMO to the Echo, and of course the Gen 24 Plus 6 to 10 kilowatts, and then of course the Tauro 50 to 100 kilowatts. So I must mention here that the control for the Gen 24 Plus and the Tauro are usually done via the WSD input because of the difference in the data communication interface card. For the SIMOs, they make use of the data manager, while the Gen24 Plus and the Tauro make use of what we call the pilot. So these will be talked more about in the subsequent slide. So to continue, I will say that the control for the SIMOs is done via the S0 input. Good. Now let's start with a typical example. So in this case, since we're using a German example, we're going to go with a German GS protection device, otherwise called the Bender GS protection. This case, we're using the Echo. So for this case, as you can see in this line diagram, contact point, we have two contactors actually integrated inside this protection device. So it has here been represented, as you can see, by K1 and K2, all connected in series. So as you can see in this case, basically all relays or all contacts have 3 terminals. So they're usually the common point, the normally open contact, and then the normally closed contact. So for this protection scheme, the normally closed contact is being used. So as you can see, terminal 11 is connected to terminal 12, which is the normally closed contact. And then since we're using the both contacts, that is K1 and K2, they are looped together via terminals 14 and 21, which is the normally open contact for K1 and the common point for K2, as you can see in this case. And then the connection is completed onto the relay by terminal 24, which happens to be the normally open contact for K2. Meanwhile, an AC to DC converter can be used in this case to provide power and buffering to the relays. So in this case, we're using a 24 volts AC-DC converter because of the specification of the relay in this particular example. So how does this work? So once there is a fault or any necessity for it to trigger, which is of course a fault, the GS protection device, of course, sends the command. So this command now definitely triggers this contact point. And of course, this now eventually brings the positive from this point to this end of the relay, thereby triggering this relay. And then this relay now triggers the internally integrated interface switch inside the inverter via the S0 switch. So that's how it works. So if you have multiple inverters, you can, of course, loop these particular contact points to their respective S0 switch, of course, via their respective externally located relays. Good. So what happens in a case where we have a combination of a Gen24 Plus, for example, and an Echo? So this is a Gen24 Plus and a snap inverter. So not much of a difference, just that each will now have its dedicated input. So we now have an input for the S0 switch using the respective scheme as explained earlier, while that of the Gen24 Plus will now be implemented using the WSD terminal. So we're going to be looking more into this to kind of explain what or how they are implemented in each case. So before that, let's now see how this can be implemented using, let's say, multiple Gen24 or a mixture of Gen24 and a Tauro. So in this case, all that needs to be done is to have them connected respectively to the WSD terminal, but then please ensure that only only the first inverter is in the master position. We're going to see that much clearly in the subsequent slide. Whilst the other multiple inverters, yes, the inverters with the other inverters, the WSD mode is in the off position or in the slave position. So let's now look at how this is done. But before that, how is this installation effected? So let's now take a look at the technical requirements. As earlier mentioned, it is advised that we observe national regulations for the selection of GS protection components for a particular system. Always clarify with the grid operator beforehand, and then ensure that for the relay, you install it inside the inverter or nearby. So it's usually recommended for snap inverters because there is usually a small space meant for additional installation that's usually made available in snap inverters. So it has a provision for a DIN rail with a width of 110 millimeters or 11 centimeters and 6.6 centimeters. So there you can comfortably install a DIN rail and then have this relay installed on it. But please ensure that the maximum ambient temperature does not exceed 70 degrees Celsius. And of course, ensure that dielectric strength between the coil and the contact of the relay is greater than 6 kilovolts. But the good thing is that most relays actually meet this particular condition. So going forward, as earlier promised, how to do this connection. For snap inverters, we'll be starting with snap inverters, how to carry out this connection. Let's give it a bit of a zoom, so for clarity's sake. Yes, so for installation of this relay, as advised to install it inside the snap inverter at the space meant or provided for it. Of course, you can have this relay installed on the DIN rail, as you can see, with your connection, the cables connected to the respective or designated points, that is the common and the normally open, as you can see. But then once this connection is done, it is expected that this cable would have to travel out to meet the S0 switch. Now, the S0 switch is actually situated on the reservoir, which is, of course, on the inverter main body or the main inverter. As you can see from this particular illustration, we can do this installation only on the wall mount bracket of the snap inverter, which of course has the DC and the AC contact points, as you can see in this case. So in order to take care of this challenge, you'd have to break out this serrated perforation. So once, because it's actually meant for cable passing of cables of devices or components that are installed on the wall mount bracket. So once you punch through this serrated opening or closure here, you can now pass the cable through. So this is how you now pass it through that particular opening after puncturing it. And then this, you can now go ahead and connect the cable to the S0 switch, as you can see in this case. And by doing that, you have successfully carried out the hardware wiring of your cable. So that's for the hardware. So after doing that, you of course have to do some configurations to activate the protection. So in order to do so, you'd have to go through the shortcut menu, the basic shortcut menu with the code. We have treated in detail how to obtain these codes. So please, in case you don't know how we got it, please endeavor to look at other webinars on our YouTube channel to find out how we get all these codes. So for the basic menu code, it is 22742. So once you have that, it is going to take you to the basic menu. Scroll to the input signal, and then next off is to select external signal. Selecting external signal meaning that we are introducing an external signal into the system. And then what are we introducing this external signal for? We want it to effect a stoppage of the inverter because the inverter needs to be turned off in the case of a fault. So what is the connection type? That is the next option you need to select. That is the normally closed. So the S0 switch will now be connected on the normally closed mode. So once it's normally closed, the inverter goes to the normally open mode and then it's disconnected. In case for those that didn't hear me, if there was a glitch in my audio, I'll just run through this. Yeah, so please go through the respective process via the input signal part. Select external signal, indicating there's an external signal coming into the system or to the inverter to effect a stoppage of the inverter because of a fault. And then the connection type is normally closed. That is what would have to be selected. Good. So continuing, we're now going to look at how this is implemented for the pilot, which is the data communication card for the Gen 24 Plus or the Tauro, as you can see. So we have a slide, a screenshot here that shows us where the WSD terminal is located, and it usually comes bridged ex-factory. So from your GS protection relay, all you need to do is to connect the two cables to the positive in and negative in. Of course, you'd have to disengage this jumper and then connect the cable to the positive plus in and then minus in. And then you have successfully done that. In the case of multiple inverters, so this is how you do it. So ensure that the first inverter is put on the on position, meaning that this WSD switch would have to be on the on position. And then for the other relays, it should all be left in the 0 position. So once this GS protection relay activates, all the inverters are going to also be activated via the first relay. So the same command or switch of command will be sent across all the inverters. So please ensure that this master-slave condition is met. Good. And the beautiful thing about this is that no special configuration is required for the Gen 24 or the Tauro, any device, any of them using the pilot. So, because all you need to do is just to do this connection, ensure that only one master exists in the system, and then you have a perfectly working GS protection system. Good. So in a case where we need to implement SPD and of course GS protection, it tends to come with a bit of something to think about. But in Fronius, we've been able to overcome this challenge by making use of two terminals on the input-output ports, as you can see here. So terminals V plus and then IN8 are implemented in this case. So for SPD or overvoltage protection type 1+2, it is of course used to the V plus and IN8 on the input-output ports are used to implement it, and then you can now have comfortably have your GS protection on the WSD function. I'm saying this because usually without a GS protection regime, it is the WSD function that is normally used for SPDs. So in a case where you want to implement both SPD and GS protection, this is what you would have to do to have a parallel function of the SPD and GS protection in an inverter. So that's basically how to go about it. So from the GS protection relay, it comes just as described in the previous slide. Then for the SPD, it comes to the V plus and IN8 terminal. Good. So as a function, the triggering of the SPD leads to a feeding limitation with the state code 1003 displayed on your monitoring device. And then with the WSD error, the WSD error message is displayed in terms of the GS protection. And then, of course, the state code that will appear on your monitoring device is 1030. And then, of course, since it is a wired shutdown command, definitely your inverter is going to be switched off, thereby protecting the inverter. Good. So how do we implement the SPD? So just a slide to show you how this is done, please. on your web user interface, ensure that you go to the input output power management and then configure terminal 8, as you can see. Then reduce the active power, activate it, and then reduce it by just 1%. That is 99%. So this basically means only 1% limitation. So this here, if it is configured this way, it will appear as a warning on your monitoring device. But then if we put it down to 0, it's now going to indicate or come up as a 0 feeding. And then of course a warning, and then inverter would eventually stop. So depending on how you want to configure it, but we would, in order to protect the system, want or recommend you going with the 0 feeding, so that of course it protects the inverter, and then the fault can therefore be checked, rectified, and then you have your system back on. Good. With that, we have come to the end of the presentation today. Let's, of course, giving you further information of how you can get info from our homepage. There you can have operating and installation instructions. Better still, you can go to our YouTube channel where you can find so many how-to and installation videos and webinar recordings. Talking about webinar recordings, you can of course, have access to a compendium of all the webinars we have conducted, including this one when it is eventually uploaded to our YouTube channel. And then, of course, you can have access to information, or whatever information you want to get from these very interesting webinars that we conduct. But better still, if you want to have direct contact with our representative, our TSAs, please do so with regards to the regions that we cover. Byron Kutzer for Southern Africa region, myself, Sipra Nokolo for the Western Africa region, and of course, David Mwangi for the Eastern Africa region. Good. So with this, we have come to the end of this webinar presentation.